Hello. In the last lesson we got acquainted with such quantities as momentum and impulse. And we found out that these quantities are very important for describing the motion of a body, especially for its interaction with other bodies. And today we will consider with you a very important law in mechanics, which describes how bodies interact in collisions and how we can describe the problems that will be encountered on our way in this section. So let's remember what Newton's second law is to describe the relationship between momentum and momentum of a force. So let me remind you that momentum is the product of the force times the time of action of this force. And due to the action of this force, the momentum of this body changes. So the question arises, what kind of force we are talking about if we are talking about some system of bodies that interact with each other? For example, it can be a situation with two bodies, which could, pushing away from each other, get some velocities. For example, it could be two carts that were initially connected by some kind of spring. And were initially at rest. After the spring began to unclench, the carts began to move apart, getting the corresponding velocities. What happens in this case in terms of velocities? Each trolley will get its own speed depending on how much mass it will have. Because, as you and I understand, a heavier body can get a lower velocity because it is more inert with respect to changes in velocities. The word inert tells us that the more inert a body is, the more difficult it is to change its speed. Therefore, with this interaction, we will get different speeds for these objects depending on their masses. Moreover, the ratio is fulfilled here, which is a direct consequence of the law we're talking about today, the law of conservation of momentum. Why is it so? The point is that when the spring begins to act on each cart and sets it in motion, a certain force, the force of elasticity on the part of the spring, acts on each cart. But by Newton's third law, you and I realize that in modulus each force will be the same to each other and in direction they will be opposite. If we sum these forces within this system, we get zero. It means that in the sum, if we summarize all forces acting on these objects, of course here we can take into account the force of gravity or the force of reaction of the support, but they also compensate each other here. It turns out that the sum of external forces, the sum of internal forces, if they are equal to zero, we will get the result that we have just seen. That is, the mass ratio will be inverse to the velocity ratio. So the law of conservation of momentum says that if the external forces acting on the system of bodies are equal to zero or compensate each other, that is, in other words, we can say that the sum of all external forces is zero. Then in this case, this parameter as momentum does not change. This is its direct consequence. And what does it mean? It means that the difference between the final momentum and the initial momentum is also zero. This leads us to another version, that the final momentum and the initial momentum in modulus and in direction, that is, their vectors will be equal to each other. But what is meant by momentum at the beginning and momentum at the end? What we are saying here is that it is not necessarily the momentum of a single body. In a system, as you and I realize, there can be several bodies. And here then we say that we should summarize all the momenta of each body and get in the end the total momentum, which will describe the whole system. Then we can say that the sum of all the momenta at the end, the vector sum, will be equal to the vector sum of all the momenta at the beginning. And thus we get a wonderful equation that will describe this system during a collision or other types of interaction. This law is called the law of conservation. Of momentum. and it is widely used not only in classical mechanics, that is, describing the interaction of macro objects such as balls, carts, but this law has shown itself very well in the physics of elementary particles, when in the process of studying the collision of these objects also managed to consider very many processes with the help of these basic laws, such as the law of conservation of momentum or law of conservation of energy. Therefore, fundamentally, when solving such problems, you and I will take into account, first of all, that this system is isolated, that is, the external forces acting on it are compensated. Of course, we cannot make them equal to zero at all, i.e., we cannot make the system acted on by other objects at all, but to compensate this action is quite a feasible task. Therefore, provided that the external forces do not act on this system in total, we will get the fulfillment of this law. Internal forces, as we have realized, cannot affect the total momentum of this system in any way. For example, since the spring acting on both bodies was triggered here, the forces were directed in different directions, their sum will be equal to zero. So in this case, this law will work exactly in such isolated systems, which we will meet with you in mechanics. And then we can describe this law in more detail in terms of what we have, for example, the value of momentum for each object at the end. So let's say this was the momentum of the first body after the collision. This was the momentum of the second body after impact. There can be quite a lot of them here. That is, we have to take into account all the bodies that participated in this collision and calculate all the momenta of these objects correctly. We do not forget that this version of equation writing can be 1 if the motion occurred along some one direction and only one coordinate of these bodies changed, for example. Or it can be a motion in the plane, that is, when you can change, say, motion in two directions and coordinates respectively in two directions. Or it can be a spatial motion where all three coordinates change. Therefore, it is necessary to take into account the components of momentum vectors on each of these axes. In practice, we will see how to apply this law and how it helps to describe such situations. That's all for now. I'll say goodbye. Goodbye.